So, good evening. Welcome to week 5. Last week we went over quite a lot of material relating to Bayesian ideas and probabilistic methods, and we ended up focusing on naive Bayes. And I promised at the end of last week that we would resume this week, going through a little bit more slowly and in more detail on the naive Bayes setup. And we're going to focus once again on the text classification setting for that. So what I plan to do is just go over the material in the next 10 or so slides and just give you a little bit of background and explain where some of the things come from, because there were some questions last time. So I think the best thing to do might just be to set things up. So we've got a couple of things we need to describe, and they're mentioned here. So we have two settings. Actually, you know, there are really a lot of settings for naive Bayes. The method has been around for so long, and people have tried so many different, I guess some of them are just, well, basically hacks. Some of them are more well-founded. And what we're going to look at here is two, I think, of the more well-founded techniques. But, you know, the basic idea can be implemented in many ways. So I don't want you to go away thinking that this is, in fact, we're going to see two ways. So, you know, clearly there is not only one way to do it, which in some ways is unsatisfactory. In other ways, I think it's realistic, because probabilistic modeling does always involve a lot of assumptions. So basically, it's just what assumptions you make will lead you to a different kind of model. So we had this last time. So we're going to go through this and figure out what's going on. So let's say we have a bunch of words, and we need to, you know, make it really elementary. So this is to say the 3 words. And we're going to start with multivariate Bernoulli. So I'm just going to show this slide, and I think not the next one, but the one after that. And then I'll jump to just, I'll do something on the overhead, and then we'll come back and talk about this. So multivariate Bernoulli, bit of a mouthful. What does it mean? Well, basically the idea here is that you're looking for modeling the occurrence of words. So basically, does the word appear? And of course, when I say word, we're just using this as an example. There's nothing intrinsic to the setup that requires text. So essentially, just think of them as Boolean features. So if in fact they were words, or, you know, some tokens, whatever they might be, 3 Boolean features, A, B, and C. And remember, in naive Bayes, what we want is, well, we obviously want probabilities, but what we want is the class conditional probability. So we're showing here theta, which is a list or a vector for these 3 features, the probability given that the class is positive. And analogously, 3 features, the probability of their occurrence given that the class is negative. So this is the naive Bayes model under the multivariate Bernoulli framework. And that's it. So how do you use this model? Well, first off, you could, you know, there are only 3 features, so you could look at the model and get some information from the probabilities. What might be an issue with looking at these probabilities in an actual naive Bayes model? Good idea, not such a good idea. So I'm saying here, so for example, if you look at the probabilities, and we have only 3 things here, we could sort of even do some interpretation or make some attempt at interpretation of, the class conditional distributions. What might be an issue with interpreting a model, such a model in this way, from your knowledge of naive Bayes? Sorry, can't hear. They may not be independent, so what effect does that possibly have? Yeah, well, overestimating, underestimating. The actual values of the probabilities need to be taken with a large pinch of salt, because, so the answer was, you're making a strong assumption that these probabilities are determined to be conditionally independent. So independent given the class. In general, that's not realistic. So yes, you could look at this, and it tells you here on the slide. So you say, well, the presence of, this is the spam classification example that we had way back in the introduction. So you could see, let's see, what are we looking at? So we're looking at the positive class, we're looking at the second feature, and it seems that this is double the probability of the, of the feature in ham. So you could, what you could say, I think, justifiably, is there seems to be more weight of evidence, which is a sort of hand-wavy, actually you can make it precise, but in this context it's a hand-wavy term. So this is more, the features have more weight. So, we're going to be essentially thinking of these as kind of linear models. Okay, so maybe B, the presence of B, is indicative of positive versus negative. So how do you do the classification? Well, X is the thing to be classified. It's going to be a bit vector. Why? Why is it a bit vector? Yep, occurrence or not of the words. If the word is present, you have this probability. If it's not present, you have 1 minus the probability. So those of you who know about Bernoulli trials will know that. I'll show you something in a second to hopefully make that clearer. And then the prediction is the product of these probabilities, or if you're taking logs, you would just add them up. And the same for negative. And so why is the... So just interpret for me this last sentence on the slide. What do we understand by that? Is positive, yep. Because? It's higher, yep. So you might think I'm being a bit picky here, but we need to be careful. So that it's the maximum likelihood because we don't have any prior here. We haven't put any prior information in here. We are doing 2 predictions, and we are picking the larger of the 2. So we're looking for a hypothesis. We don't actually have a probability on the hypothesis, right? So we're just doing this argmax. Remember that from the Bayesian setup. Because we're doing classification. It would be nice to have a probability, but all we've done at this point is calculate estimate which is the more likely hypothesis for that data point. Okay, so skipping over that, which we'll come back to. Second framework is the so-called multinomial. The setup is very similar. Now, we've got to be careful here. So this is, I'll show you how to interpret this shortly. It's not as straightforward, I don't think, although essentially, as we'll see, the models are very similar. So here we have probabilities again. So this is still a vector of probabilities. But what the data is, well, let's just explain this. We have a new, we have a data item. This time it's not a bit vector, it's a word count vector. In fact, very commonly in text classification, you have different ways of doing the word counts. But let's assume this is simple word counting. So we've got 3 of A, 1 of B, and none of C. So the total is 4. Okay, so now the multinomial model, you can see the framework is the same, right? So we do that what if. So what if it was plus? What would the probability of x be, given that it is plus? What if it was minus? What would the probability of x be? So basically, we need to plug in our word count vector into this and this. But we do it in a what looks at first glance a little bit more forbidding approach. We're going to go to the overhead in a second, and I'll try and dig into that a bit more deeply. Some of you may know this, so if you do, apologies, this will just be review. For others, hopefully it will clarify. And the point here is that you have a different model, so you may get the same prediction, but in this case it turns out that you don't. The ML classification here is the opposite. And there's a little note here which is suggesting that when you have word counts, in some sense, it's a different kind of evidence, so it will give you a different kind of prediction. Okay, so I promised you some details. If I can just read my own handwriting, let's try and see if we can explain this. Now, I need to get this right. I think what I need to do, so this is really for the guys watching on the video, so hopefully I get the right projector. Just give me a sec here. So we want the document camera on 1. I think that's what we have to do. Because otherwise, I think people don't see on the video the thing we're doing here. So those of you in the room, no, we don't want to do that. Those of you in the room should be able to see this as well as seeing the... Okay, so let's flip back to... So people in the room, you should now be able to see the multivariate Bernoulli. So I wrote down a bunch of stuff about multivariate Bernoulli. So again, some of you will know this, so I won't take too long, but we have this idea of a Bernoulli distribution. Can you hear the microphone? Can you hear the back? Okay. Is that coming out? Okay. All right. So we have the idea of a Bernoulli distribution. I'll just abbreviate that like that. And the key idea is that we're modeling anything that has a binary Boolean outcome. So we have a set of outcomes, and I'll just call them no or yes. Okay, so this is binary classification. So binary classification. Now, what we're interested in is the probability of success. So a yes, or whichever outcome you pick. And you imagine that this is a sort of setting where you can, do stuff. So we call that a trial or an experiment. And the probability of success in this distribution is just a single probability, theta. So to be more precise, we have the probability that we have some variable of interest, a random variable. Probability is yes, because that's success, is theta, and then the probability that the random variable, whatever it is that we're testing, it just denotes the experiment or the trial, is no, is the opposite, 1 minus theta. So these are called Bernoulli trials. So you might be saying, okay, so far so good, but what we can then do is model the... Well, actually, before I do that, let me just note a second distribution. So this idea can be generalized to the case where you have k outcomes, where k is not restricted to 2, so k can be more than 2 or more. Discrete outcomes. And this will give you something that goes by the name of the categorical distribution. At least this seems to be the usage in machine learning. So there we now have the parameters of this distribution as a vector, and we have a theta for the first and the second, and so forth up to k. So you can probably tell where this is going in terms of text and words, and this has to be a distribution so that over the k outcomes, we'll index into that using I. All of the parameters sum up to 1. So, and we'll assume that probabilities are probabilities. So we have then this idea of categorical trials. So this is the sort of base of the probabilistic machinery that's going on with these two frameworks. Now I'll see if I can squeeze in what we need. So we need to know that. We need to know first off what. So we need to think of this in terms of not just distributions, but how you actually use them to model words in text documents. So the first one we had was called multivariate Bernoulli. Multivariate Bernoulli. Okay, so this guy here, informally, it's, I'll just sort of write something in language. So for the ith word in the vocabulary, so the vocabulary we need to fix, because this is like our feature set, does word I occur in the document? Word I occur, right, in the document, assumingly, or the text or whatever. So we then have the model, as you saw, is, well, we'll call it X, vector of random variables, modeling the presence or occurrence. So this is this kind of thing here, right? So, and the model is the I won't write that down, but the model is going to be, so if we have k words in the vocabulary, this is the distribution on these random variables represent the words that can appear in documents with a certain probability. So any multivariate Bernoulli model is going to have that form. Okay, so the other one that we had is the multinomial. Multinomial distribution. This is a multivariate Bernoulli distribution. I haven't put down the word distribution, but the multinomial distribution. Okay, so this needs the following. So we have what we can think of in the context of text classification, a word count vector. Okay, so we'll do it like this. So we have a random variable x1, big X1, equals little x1. Little x1, well, let me just write out this. So we have x2 equals little x2, and so forth, up to xk, the random variable, equals the value xk. So what does this mean? Well, The big ones are the random variables, and the little ones in the context of text, and since that's what we're talking about, I'll just put this in. This is the word count. The number of occurrences of the word. So this is the thing. So here these are bit vectors. Here these are word counts. So the distribution, is this going to fit? Yeah, I should be able to just squeeze it in at the bottom. The word count vectors are going to be modeled like this. So this is going to get a little bit... oh, there's one thing I forgot to do. Sorry, let me go back. I forgot to put in the setting where we have the binomial distribution, which I think you'll all be familiar with. So this is based on Bernoulli trials. So the well-known binomial distribution, which everyone has seen, is defined as, well, let's say we have n things and we have r successes, if you like. So we have n experiments is what this means, n trials, if you like, and then r of them are the ones of interest, which I think we're thinking is yes. And the distribution on this for any values of n and r is like this. We have the single parameter. Did I say it was theta? Yes, I did use theta. That's good. So this is that number of successes. And then, so why is this to the r? Well, every success is independent, and so you multiply the probabilities together. And then 1 minus r, which is the ones that are not successes. Sorry, my bad. 1 minus theta to n minus r. Right, the ones that are not successes. So that's the binomial. So it's useful to bear that in mind when we talk about the multinomial, because the multinomial has a different form, but essentially a related idea. So what we want to say is the probability that the vector of word counts x1, so this is little x, these are the word counts, x2, up to, what was it, xk? So the probability that the random variable, which is this vector that you know is the universe of word counts, is like this, is the thing that we saw in the slides, essentially. So n, where n, I'll say what n is, it's the total number of words, n factorial, and then we have these parameters from the categorical distribution. So theta 1 is the probability for word 1 in the model, to the power the number of times you see word 1, divided by the count factorial, and then I'll just put in some, I'll just use that to make it clear that it's multiplying together. I'll do one more, that's theta 2 to the power of the word count over factorial of the word count times ... times the kth, which is going to be like this. Sorry, that's k. And we need that all of the word counts obviously add up to the total, which is word counts of the xi's, and they sum to n. Now, I'm not going to go into the details anymore of the multinomial and the multivariate Bernoulli. The important point is, yeah, it's all on, okay. Hopefully everyone can see that. The important point is that in both cases, we end up with the thing that we saw on the slides, okay? So the, I didn't draw out the distribution for the multivariate Bernoulli because I think it's pretty straightforward. But the multinomial looks a little bit forbidding or confusing, but it's essentially the same form as we see for the binomial. So the way to think of this is that multivariate Bernoulli, you have multiple occurrences of Bernoulli trials. Does the word occur or not? Right, so multiple words. For the multinomial distribution, you have multiple occurrences of word counts. Okay, so and the probability of something with that number of outcomes is governed by this distribution here. So the two formats, the key thing here is the two formats are the same. The probabilistic model is different. We're showing you how to calculate in each case the naive Bayes, well actually on the slides, we're showing you how to calculate in each case the slides. There's one more thing that you need, which we haven't got to yet, but I'll do that in a second. Are there any questions about this before we continue? Any questions? All good? Yes?
I noticed that when it's counting the occurrences of the word, it seems to, correct me if I'm wrong, but it looks like it sees the word like twice. It considers that to be like the product of the probability of seeing it once. But in practice...
Hang on. Sorry, the product of the probability of seeing it once.
I mean, maybe I misread it, but if it, say there's a 1 in n probability of seeing the word once, does it then say seeing it twice would be like a 1 in n squared possibility? Is that
Yeah, that's correct.
I'm just thinking that in practice, like if you do actually see a word once, it's extremely likely you'll see it again. Like what I mean is like the word battleship, for instance, might be unlikely to occur in any given text, but if you see it once, it obviously becomes much more likely that you'll see it again because it's probably a book about, naval history or whatever.
Yeah, what you say is true, but so what's the problem? I mean, say battleship was word 2, you'd be anding together all of those, which is multiplying them together. So if I see, 5 instances of battleship, it's whatever you said, one over, whatever it was you said, to the 5. Yeah. But that's what you should do for any word. You should, if you're going to take the probabilities of the words as a vector, then you're anding all of them together. So it's this word and so what's the probability of me seeing this word and this word and this word? So if I see any word repeated, you're just going to have to do that.
I understand that naive Bayes means that it assumes that the words are
Yes.
independent,
Which we know is not true.
But in practice you can get away with it.
Sometimes, yeah.
I'm just thinking that multiple occurrences of the same word are probably one case where that's especially damaging, simply because if you do see the word once, you want to see it again are vastly increased.
Yeah, possibly. Okay, here maybe a couple of comments. First comment is it may not actually, if you see the same word multiple times, it may not be such an important violation of independence compared to, say, seeing a certain sequence of words multiple times. So there might be more, actually, that might be worse. Second point, probably more important, is that this is all, you've got to remember, this is all done in a class conditional fashion, right? So this distribution here for battleship, in your example, if you were trying to classify, say, news articles as being about, war rather than sport, it wouldn't matter so much if the estimations were off again, as long as, things are going to work out, because battleship's going to be pretty infrequent in sport. So you're still going to see a signal dependent on the word count. But if the class conditional probability, let's say theta 2, so the key thing is theta 2 in, what did we say? War versus sports should be higher. So if you add them all together in the class of interest, you should still come out better than in the other class. But I'll take your comment as a general comment on the sort of weakness of the model as a language model, which is certainly well taken. That's a good point. Any other questions about this? So all I want you to really focus on is this is a sort of expansion of what's in the slides. There's one more thing we need to do to get the example working, which is the pseudocount problem. But if everyone's happy with this, I'll just get on to the likelihood problem. So I'm now going to put the slides back. I need to be careful. Just give me a second. So I need to put everything back on projector 1. For the people in the room, I might put on projector 2 the document camera. So hopefully people on the video are now seeing the slide, and people in the room are now seeing the slide on one and the overhead on the other. So let's get back to it. So where were we? Okay. So just something quickly on, I mean, this is not really necessary for naive Bayes, so I'm not going to spend too much time on it. But there is something I think interesting here, which is that what you're actually doing with naive Bayes, and it's very obvious in the two-class case, is the relative likelihood. And the classic way to do that is the likelihood ratio, or even the odds of the likelihood ratio. So the likelihood ratio here for the two, this is the multivariate Bernoulli. So we have this, I believe that's correct. So the numbers come out, you could just do this with fractions, the numbers would come out like this. So 3 over 2, which, let's just check, corresponds to the direction in which we're predicting, which is positive. So positive in the denominator is larger. But now remember we said there were no priors in use in this prediction. But this tells us something interesting about what prior information, what effect prior information would have. And it's basically written out here. So if the prior odds, plus is spam, right? So this is a prediction of spam, positive class. But if we have a prior, which is being shown down here, just the prior odds is the ratio of the prior of positive, the prior of negative. How do we find the priors? Yeah, it's even easier than that. We just have to what? Well, we just count count the relative frequency of the two classes in the data set. Yeah. So we got a bunch of positive labels and we got a bunch of negative labels, and we just take those as probabilities. So depending on the prior, this can change the classification. So for example, here, if we have 3 over 2, so the prior odds are more than 2 over 3, then you're still going to get spam. But here's a case where they're not, so they're 1 over 2. So if you multiply through by the prior, and remember, well, I'll just say something about that in a second. If you multiply through by the prior, this is what you're going to get. So this is now less than 1. So you're going to predict in the opposite direction. So what does this mean? Well, remember we said the sort of basic idea with naive Bayes is you have the prior and then these independent likelihoods. So the prior can definitely have an effect. In fact, some people apply naive Bayes without the prior, because if the class ratio, positive to negative or the other way around, is very skewed, and it often can be, like, you can have 90% in one class or more, then that could have, depending on your data, quite a strong effect, and it might actually be quite difficult to get good predictions. So the role of the prior is quite important. So some people sometimes just leave out the prior and basically just do this. So that's okay. You're just doing a likelihood ratio, but if you want to be a bit more Bayesian about it, naive Bayesian, then you'd do this. All right, so now back to the multinomial. So now we've seen where this comes from. So this is the probability. Here's our probability parameters, which is what we said we needed. And then the vector x has these word counts, so we plug those in. So there are 3, 1, and 0 respectively, and we get out this, this here. So the ratio, likelihood ratio, the thing we've just been looking at, comes out to be that. Are there any questions now about this? Because I think there were last time. Is everyone quite clear? Yep.
Sorry, going back to the last slide.
Oh, sorry. Okay, this one? Yep.
Yeah, so is it okay to use likelihood that if you know it's skewed and your prior is probably worse?
Likelihood you would use because that's all you have. That's your data, right? So
Can't you estimate the prior is based on the data then?
well, the prior here is just the prior of the labels. So I think you're thinking of a richer model class where you would have priors on the, let's say, the random variables for the words, which you can have, but this is even simpler than this. This is just a class prior, right? We're going to look at something which is kind of like a prior for words. It's based on the pseudocount idea I showed you last time. But it's not a very sophisticated prior. It's essentially to do with missing data. Yep.
So without the prior information, can we still call this Bayesian classifier?
Not really. That's an excellent point. So the point here was, for those who didn't hear it, without the prior information, can you call it Bayesian? Strictly speaking, no. You're right. But since this is quite a long way from being sort of proper Bayesian anyway, I think we can, if we've allowed ourselves to call it naive Bayes, we can continue calling it Bayes. But you're right. It's not. It's a likelihood based approach. Right. So everyone's very happy with this. Okay, good. How are we doing? So I don't think there's anything particularly. Oh, sorry. That's weird. I don't think there's anything particularly more to say to this. So we now understand where all of these factorials and so forth come from. The key difference being the word count, and we can also get a likelihood ratio. Could we do the prior here, the thing that we did before, with the multivariate Bernoulli? Could we put a prior in here? Why not? Yeah, you could. This is the same thing. All right, let's look at an example, because there's one more sort of minor but important issue. I don't want to take too long on this. Let me see if I can jump ahead. So here's so these are supposedly emails, and there are a bunch of slides that are all sort of related. So I'll move back and forth within them. So these are, let's see, there are 8 and 4 in each class. These are word counts. So this is the bit vector version. They should match up. So how would those vectors have been arrived at? Well, notionally something like the following. We've got two sets of documents. They're short, it could be, I don't know, even too short for emails, so they could be sort of micro tweets or something. And a bunch of, there are actually 5 symbols here, and a bunch of them are regarded as being of interest. So, well, it says here stop words. Stop words is just something that, words that are sort of essentially not class conditionally interesting, right? So their probabilities won't help you to predict anything. So you get rid of them. So frequently occurring words, or actually maybe sometimes you'd also get rid of very infrequently occurring words. So A, B, and C are the vocabulary. Okay, so we know that we need a count vector if we're going to do multinomial naive Bayes. So what actually happens is the following. So remember we said that all of the word counts need to sum to n. So we're told that there were 5 of the first word, 9 of the second, and 3 of the third in the plus class, which is spam, and another bunch for the negative class. So there's one further thing that needs to be done, and it's this prior or pseudo count. So a pseudo count is a simple form of prior. I showed you a more complex one before called the M estimate. You can refer back to that to see why that is a prior. I'm not going to go over that again. But here what's done, so you see here, the probabilities now look different from here. Okay, so n is 17, and I think coincidentally 17 for these. So here we have 6 out of 20. Where does this 6 come from? Well, if we remember actually it's still up there, so people in the room can still see it. So we've got n words. Now, what we actually do is we add 1 over n to each actual probability, right? So these are, so in the model, so like over here, these thetas, these are in the model, but we have to estimate them from data. So to avoid issues of missing values, particularly when there are no words, but also to generally smooth the model, we say there's always at least one occurrence of the word, so we never have 0 occurrences of the word. And to make that correct, then we need to add, this is for theta, so forget the, theta 1 to the x1, just for theta itself. To estimate theta, we count up the number of occurrences of the word 1 in the positive class, starting from 1, right? So we say there's always at least 1 occurrence. Then we see another actual occurrence, that becomes 2. And then, because we're adding essentially all of the words in the vocabulary, we have to, in the denominator of our estimate, we have to start with the n words, right? So before you start counting words, everything gets 1 over n as the probability. So it's like a uniform prior, as you were asking about. Very simple, very elementary prior, non-informative in this case. And that's where these numbers come from. Okay, this, whoops, sorry, I've gone back one. So if you're wondering why it's 6 over 20 and not 5 over 17, that's why. Is that clear? Why did we get to 20? Excellent. Answer is 17 plus 3. There are 3 words in our vocabulary, and why is it 6? Yeah, 5 plus 1. So 5 actual occurrences plus the 1 that's always there. Make sense? Anyone? Good. Okay. Because if I have n words in my vocabulary, the prior for multinomial is 1 over n, right? So I had 1. So here, 6 over 20. I have 17. Words. I remember I'm just doing this for positive and negative separately, but here I have 17 words n is 17. Plus 3. N is, sorry, did I say N? I meant K. My bad. My bad. Someone saw through my mistake, yes. I should have said K. Sorry. Let me just make that quite clear. N is the number of words in the document, but we have a vocabulary of size K. So when I've been saying 1 over N, I should have said size K. Sorry, that probably screwed you up. Does that make sense now? Okay. Yeah. Sorry, the prior is 1 over K, 1 over the size of the vocabulary. Right, so we start counting from 1 over K, sorry, 1 over K plus N, 1 over K plus N, 1 over K plus N. Dear, 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 I should have written this down. Is anyone confused by my misleading statement? You still on board? That's why it's 20, 1 over K plus N. All right, it's actually easier for, it's actually explained here, but anyway, that's what we get. And I think it's explained for multivariate Bernoulli. Okay, so, and just to be clear, here are the raw counts. So it was 5, that's where the 5 comes from, and so forth, right? So that's where, and then we add the smoothing values to get that right. For multivariate Bernoulli, it's more straightforward. Essentially, it's we add 1 to the numerator and 2 to the denominator, because each one has can either succeed or not succeed, because each one is a Bernoulli trial. So let's just check. So we have two occurrences of 2. 3, it's 2 occurrences of A, 3 of B, 1 of C, and so forth. But actually what we estimate the probability as is 3 over 6. So why 3 over 6? Well, we add 1 for the pseudo count for the word, so we always start from 1, so we never have 0. And there are 2 possible occurrences, either the word occurred or the word didn't occur, so we add 2. So here, there are 2 occurrences of A, but we start from 1, and then we need to add 2 to the denominator. And so we end up with 3 over 6 and so forth. Now, it says down here, so you might be wondering, well, why do I add 2? I explained it in terms of the Bernoulli, which I think makes more sense. But you sometimes see this. So notionally, what you're adding to all of the, to any data set is 2 so-called pseudo-documents, 1 containing each word and 1 containing none of them. I don't know if that helps. I think it's actually sometimes a little bit more confusing. I think you're okay if you remember add 1 to the numerator and add 2 to the denominator. In the case of the multivariate Bernoulli, this is known as the Laplace correction, which is sometimes the way it's explained. Okay, any final questions about that? All right. Yeah. For the Bernoulli version, if it's just a bit vector, yeah. Yeah, 1. Yeah. Is that it could be a typo. Let me see. You should be, so you treat them independently, positive and negative. You should have added 1 to the denominator for all of them and 2 to the, sorry, 1 to the numerator for all of them and 2 to the denominator. Yeah, no, that's, yeah, that's okay. That's okay. Okay. Oh, I see what you mean. Yeah. Okay. Yeah. No, I think you're right. That looks wrong. Yeah. Okay. Typo. Yeah. Good spot. I think that's wrong. I'll check that, but looking at it now, I think you're right. Good catch. Anything else? Yep. Okay, so, well, it was just pointed out by a couple of members of the group. So the idea here is that you add one, so you always start from one on the word count. But there are two possibilities. Okay, so there are a few different ways to understand it. So one is, I think the easiest way is just to say, well, for a Bernoulli trial, there are two outcomes, and you're saying one of them always occurs. Another way of saying it is, oh, it's called the Laplace correction, and you just remember that. A third way of saying is, here, you're adding two pseudo-documents, one containing each word, and one containing none of them. Okay, so every time you add up, so you're dividing by the number of documents in order to get an estimate of the probability. So you add two, okay? But as was just pointed out here, we've got a different number of bit vectors here.
I think it is right. 4 refers to the number of documents in the previous slide, 8 positive and negative, so it's 8.
Right. Yeah. Sorry. Yeah. No, I just realized that as you were talking. Yeah. Okay, so that's right. Okay, so this is 2 out of 4 plus 1 out of 2. So you get 3 out of 6. This is 3 out of 4 plus 1 over 2. So you get 4 out of 6. Yeah. Thank you. Does that make sense? No? Okay, so let's just pick the first word in each one. So 2 occurrences. So each document, let's go back to the data. So each document can either, let's just take one column, we'll take A. Each document, it can either have 1 or 0. So here we have 2 occurrences. So 2 out of 4 possible trials, it occurred. Add 1, because you don't want to have any zeros here. So say this column was all zeros, you'd start counting from 1. So this is actually going to be 3. And then the 2 possible other occurrences are a 0 and a 1, the 2 possible outcomes. So you add 2 for that. So 4 plus 6, or whatever this number of documents plus 2. Right, so 2 over 4, 2 plus 1 gives you 3, 4 plus 2 gives you 6. For this one here, you get 3, add 1, you get 4. 4 documents plus 2 equals 6. So this one is 4 over 6. This one was 3 over 6. Yep. Right. Thank you for the help from the group. Any other?
So I can still show you the 6. So I know you got the 4.
Okay, with this one, no, these are good questions because I tripped myself up. So with this one, what's the probability? Well, we've only got in any piece of text, it can only occur or not. Okay, so if I have n trials or things that I look at, I can only have, the maximum number of things I can have is n occurrences. Before, in the multinomial, I was counting word occurrences. So I could have more word occurrences than there are documents. But here I can only have it occurred at least once or not. So the estimate, if we're turning the relative frequency into probability, the estimate is the denominator for multivariate Bernoulli has to be the number of documents, whereas before it has to be the number of words. What the pseudocount thing is doing is notionally saying essentially the prior probability of seeing a word occur is 1/2. That's, I think, the easiest way to see it. You can use this pseudo document idea if you like, but I think that's really the best way to remember it. So if I say 1/2, turning that into a relative frequency 1/2, and then I just add the actual occurrences to the numerator, and I add the number of documents to the denominator, and then I take the fraction, and that's my estimated probability. So I'm adding, if you like, I'm always counting from 1/2. So if I have no occurrences, I'm downweighting my prior by the number of documents. Okay, so it was actually 1/2, and then I add the number of documents, and it's now, n documents. So I get a very low value, but non-zero. That's the minimum value I can have. Is that making sense? Is that helping? Does anyone else not see what the relative frequency story here is for the two different things? All good, okay. So just remember, multinomial, word counts. So I need to take my frequencies out of the number of words in the whichever class I'm looking at. For multivariate Bernoulli, it's how many times it occurs over the whole set of documents. And I can only say it occurs or it doesn't occur. So I have to divide by the number of documents. So the two different frequencies, one is taken out of a total number of words, the other is taken out of a total number of documents. Does that help? No? Okay, think about it. If you're still not sure, ask me next time. Let's take a break, and we'll resume. I'll put a timer on so I don't go over time this time. Do you want to, sorry, let me switch this off. Sorry, I just have to put the timer on because I tend to talk to people and go over time, and that's not good. So just let me put a timer on. Say for 8 minutes. Okay. You need an extension?
Yeah, since we got the answer, does TXT that file later?
Okay, so I'm getting more requests for this. So I can tell you now, I think I'm going to extend it by 2 days. If you need more time, I need to talk to the guys who are doing the assignment setup. But I'm probably going to do that. If you need more time, send me an email because some people that won't be enough time.
One of the questions is also about the decisions. We haven't really gone through it.
That's true. Yeah. No. I will. We're going to extend it to Wednesday.
The thing is, we're going to have a consultation during the break since the midterm is going to come.
Okay, so the midterm is, we hit a bit of a problem with the midterm. Basically, the class, I haven't been able to find I can't find anywhere big enough to take the whole class. So I'm still trying to work it out. I still think it's going to be week 6, but it's not 100% definite. It might have to be pushed back. So in the next couple of days, that decision will come out to you. But yeah, consultations, there will be time to do consultations.
Another question about this. So in this case, if we got the same number for each class, that means the prior distribution tells us nothing, right? Since we got a number for each class.
It's equal. It tells you nothing, yeah. It tells you nothing, yeah.
It should be 6.5.
What's wrong?
Yeah, it should be 6.5.
What's the error?
Like the code is not runnable on the computer.
No, you don't run it on the computer. You don't run.
It doesn't work from my Jupyter notebook.
Why not?
it keeps saying the error, and like the error because of the end of something.
Oh,
And like it says I search online, say because it's.
Have you
not-
got Python 3?
because like she's
That's why
using
I'm
like
not
7.6.4, and the version we are using is probably like 3.6.5.
There's almost
But
nothing. There's almost nothing there that should. The Python version should make almost no difference. I mean,
Yeah, I'm downloading the like Python 3 version right now. Anaconda 3. I used to do Anaconda 2, and it
Maybe
didn't
just
work.
need to use pipe install, pipe update, more easier way to.
I did, and it didn't work.
Oh,
I did the Pi update.
Type 3 update, you sure?
Yes,
Or try the homebrew.
I did. You see, they said like how to change the version in Anaconda, and like my Anaconda, as you can see,
That seems very interesting. I think the one is runnable now.
I don't know. I just thought,
.bshrc.
yeah.
No, I think it's called something like bash profile. Yeah,
You see, the Anaconda
Yeah.
has already been changed the past,
yeah, you have already changed it.
and when I type Jupyter Notebook, it doesn't work.
have you tried Conda? So how did you install? No, did you install the notebooks via Anaconda?
And I run the program like it can show the table, right? But when I
But it
try
should
to
like
run,
open up the web
oh
browser.
yeah. I'm waiting. It's been longer.
Oh.
Okay.
Or just copy the coding to your IDE.
I
It works fine.
No, I don't think that'll work.
No, you
No,
have to
it
use
doesn't work.
Jupyter.
I don't know why. How do I do my assignment?
Well, I just
I hate typing.
relax,
right?
relax,
I
relax.
think you can use a lab
It's
computer,
still
right?
on 2nd of April.
I'm almost certainly going to move it till the 4th.
Both. It's only 2 days more.
If you need an extension, let me know.
No.
Don't panic.
You see? I don't know it works right now. No.
Okay, try run all.
This one.
Yep. What's the arrow?
Wait. This one?
Oh, import.
I
You
did.
haven't
I
installed.
installed in Python 3 just few minutes ago.
Hang on.
I installed this one for Pipe 3
No, but you haven't
Did you
installed
do pip,
ARFF.
did you do pip
in my terminal.
like
Pip 3 and like Pip 3 in
Try installing that one.
which one?
Try installing this one. ARF.
it's up here. You have to
Yes,
just
I
copy.
did. You can see.
Did you do that?
Yes, I did Pipe 3 and Pipe over both of them. You see? Oh, you see. I haven't like this is the original one. I already downloaded like few minutes ago, and like it still doesn't work.
No, that's not right. It has to be this.
Try this one.
Has to be this.
Yeah.
Well, I'm not sure about the pip version, but it has to be LIAC.
Yes. Go for pip3 because pip2 like will
I did
store
both of them.
things into your Python 2
Okay.
It's already
library.
Okay, do pip3 install liac.arf. LIAC dash AC.
Dash
LI.
ARF.
That looks okay.
Yeah. And
Run the game.
no, we run the kernel.
You have to.
We run the kernel.
You can go.
Restart.
You go to this one. Pick restart. Wait a minute.
No, I have this,
Restart kernel. Clear out. Confirm restart kernel. Run all cells. Try that one.
Restart.
Yep.
Did it work?
Select all
Oh, select all.
and run it. Yeah.
No waiting. Wait.
What's wrong?
Go back up.
Oh.
Why?
Do you have the data sets in your Where's your directory? Go back to your shell,
Oh, I didn't
your
put
terminal.
it- I forget to put them into a same directory.
Nice question. Is it a typo here? It should be like
No, it's okay. I thought it was a typo because I wasn't thinking straight. But then what it is this.
yeah, why is
data
six? Why is six?
And
But
this is-
it's 20.
I
While
need to
we
grab
did
inside,
it in
right?
20 is the word count version.
What about this one? This is
Okay, cool.
what's the difference between them?
Okay, so well, that's what we were just talking about. So the word count version, the frequencies are the probabilities are estimated over the number of words.
And then it should work.
With the bit vector one, the probabilities are estimated over the number of documents, right? So so the number of words is larger, so that gets you to 20 because you have to add the extra words.
Yeah, but for the bit vector, well, we don't just add those numbers.
You do, but you add the
Wait,
you add the.
let me do it again.
No, I have to start again. So this here, you count one. You add one for each word, and then you add 2 to the numerator, to the denominator. Okay, so there are 4 documents plus 2 gives you 6. 4 documents in this data set, right? 4 documents. In plus. 4 plus and 4 minus.
Okay, we have 4 documents.
Yeah. So I have 4 documents, and I can only have if my probability is 1 of seeing the words, it would be 4 out of 4. Okay. But I never want to get to 0 or 1, so I add 1 to the word count and 2 to the denominator. 1 to the number of occurrences and 2 to the denominator. So I start with 1/2, and then I either go down to 0 or close to 1. So 4 plus 2 is 6. So if I had 20 positives, it would be 22. Okay, so it's the number of documents.
So which needs to count the number of documents?
Yeah, the number of occurrences over the number of documents. Plus 2 in the bottom, plus 1 on the top.
For this equation, the multi-value binomial distribution, no, Bernoulli distribution, on the numerator we have alpha. I just want to know, like, what does each theta represent for?
This is the probability of seeing the word
Random
out of
variable?
yeah. So out of all of the words, what's the probability of seeing that word?
Oh, it's like, so why is like theta divided by x2?
No, it's theta to the power x2 because x2 is the number of times that. So theta 2.
Theta to the power of x2.
Yeah. So it's like here, right? So here I have well here in the binomial, right? So n choose r. Theta is the number of times I see the thing to the power r, which is the number of times it actually occurred.
Right.
So here it's the probability of seeing that word and that word and that word to the power, the number of times it actually occurs in the document.
But like on the numerator, we have like the factorial of x1 to
The,
xk.
the denominator is
But
the
like, I think x1 is like a random variable, so
no x1 no. Big X1 is a random variable. Little x1 is the number of times that
Number
word
of
occurs. Yeah.
oh, so
So
like,
the probability is this random variable, which is a word count, for what's the probability that I actually see that number of words?
oh, so like we have to. But why is the factorial? Why does the factorial make sense?
It's well,
Like,
that's kind of beyond the scope of what we're doing. But if you want to think about it in the same terms as the binomial, it is the number of ways you can choose that many number of successes out of n trials. So it's the number of ways I can see that many out of that count. But that's getting a bit too complicated for what we need. You just need to know that the shape of the distribution depends on the probability and the word count.
I got it. Thank you very much.
Okay. Can we come back later? Thanks for your help back there. That was great. Yeah.
In the next, is that week 6?
We got a bit of a problem with numbers, and I'm still trying to sort out venues. I'm going to be emailing tomorrow, I think, once I know where the venue's going to be. Yeah. Okay, we're back. Okay, so the last in our set of base level classifiers are the pure linear ones. Now, I will say that under certain interpretations, you can view naive Bayes as a linear classifier, but we won't spend time doing that. Nearest neighbor, under certain conditions, can also be viewed as a linear classifier. So in some sense, all of these methods are potentially viewable as linear. But the ones I want to finish off with are definitely linear. That's part of their structure. So the first one I'm actually not going to talk about, which is widely used. It's a classic method in statistics. We mentioned it in the introductory lecture where we called it the basic linear classifier. And I mentioned it at the start of this lecture as well. It's essentially finding the mean of the positive points in the centroid in a high dimensional space, and the centroid of the negative points, drawing a line between them and finding the perpendicular bisector. And I mean, it's not as simple as that, but you can think of it in those terms. It's not widely used in machine learning. It's a classic method from statistics, but it is a representative of this class called linear discriminants. The second one is a method called logistic regression, which is sort of a version of regression, but is probably better thought of as a probabilistic linear classifier. And we'll briefly explain that. And then I'll spend a little more time talking about a third method called the perceptron, which you may have heard of. Right. So we mentioned when we talked about linear regression, we mentioned that spent a lot of time developing the linear model idea, which is basically this: W transpose X, where X is your data. So in a d-dimensional space, these are all real values, and then you have a weight vector of the corresponding dimension. And the problem here is using that kind of linear model, regression type model, but for classification. Now, there are actually lots of ways that people do that, but they're beyond the scope of what we're doing here. This one, though, is designed to classify on the basis of the probability of being in one class versus the other class. So the probability of y equals 1 versus 1 minus the probability of y equals 1. Now, the formula that is used here is the so-called sigmoid, or logistic function, which has the form, well, it has different forms, but this is the classic form, 1 over 1 plus e to the minus the parameter. Okay, so the parameter here is determined to be modeled as this linear expression. So another way of thinking about what this is, here's the linear model if you like, is the probability that y equals 1 given x over 1 minus that. So you You can actually think of that as an odds ratio in the sense that we've just been talking about. Note that it's not a likelihood, it's a sort of, it's the actual thing that we want to predict, the class, in terms of the x, not the other way around. Take the log of this ratio, and this turns out to be linear. So the log of the odds ratio, if you like, in terms of favoring the class versus its opposite, is linear. So that's the sense in which logistic regression is linear. The logit transform is what you're doing, so this is linear for the logit, but the thing you actually want is this thing here, so this is the correct expression. Now to actually fit this, well, there are many ways that you could fit it, but for example, gradient descent type approaches. But we won't spend any time going over how that is fitted. The one last thing I want to note is that there's a multiple class version of this, which you may have seen. This instead of the logic, there's something called the softmax, which generalizes to multiple classes. So you'll often see logistic regression, for example, in the final layer or even lower layers of neural networks. You can think of those as doing something like a logistic regression. Any questions about this? Have you seen this before? No. Okay, it's a classic method. Personally, in practice, I haven't really ever found it to be that useful. There are usually, I find, other methods that work better. That's my experience. It's worth knowing about. So the way to remember it is just it's a linear model like regression, but for classification. All right. What I do want to spend a bit more time on is the perceptron, and that's for a few reasons. It is a linear classifier. It's trainable in quite a straightforward way, but one that has some actually appealing properties. And we'll talk about those. Now, it's a very long-standing method, and it's of interest basically because it is representative of a class of methods. And the most famous of the class of methods that it represents is, of course, the multi-layer perceptron, which has been generalized into deep learning. The multi-layer perceptron idea is very, very widely used, as you would know, and we'll talk about that another time. But the perceptron itself is surprisingly still useful in some contexts, and certainly it's important to understand how it works and, in fact, why it would work. So the perceptron actually was a system when it was first built. There's a key idea, which is that of linear separation, which we've mentioned before. This is a picture that's widely available online. I haven't actually determined what it refers to, but I think what it refers to is a publicity photo. You can see a TV company logo here. You can see a shape sort of recognition task over here. I think that's what that is. You can see something here which looks like a grid of sensors. I believe that's what it is. This is a bunch of wires, I think, and this, I think, is the guy who implemented it. Now, interestingly enough, the perceptron itself was not envisaged as a single unit alone. It was actually always designed to be a multiple, well, not so much a multiple layer, but the multiple perceptual units in the perceptron. And I think it's pretty nice that you can actually see over here the hardware. I believe these are the potentiometers that are referred to. And this looks pretty cool. So you got to remember, this sort of room-sized device had very limited computational power. So to the extent that learning could take place, it would have to be pretty elementary. But we'll see, surprisingly useful, at least in concept. So here's the system. So we have a bunch of inputs, so sensors like on that picture. Obviously, you think of this perceptron architecture in terms of sensory perceptual tasks. So, you could say these are pixels, or they could be channels in an audio system or whatever. Anyway, you have a finite number of them, 1 to n. Each one has a connection to, in this case, a summing unit. The connections, the edges in the graph, if you like, have weights on them. So for these inputs, these weights are essentially the model. Now, typically, we also have a fixed input, which is the 0th input, and that is fixed at 1. And that also has a weight. And this represents, in terms of the familiar linear model structure, this represents the offset. So once the summation units in hardware or software is applied, then what you have at this point is the sum of the weights times the inputs for each of these, 0 to n. And then this, at that point, actually, you have a functional system. It can do stuff, right? So it's got a linear model, and this will be an output. So you could do something here. We'll talk about that in a follow-up lecture. But over here, because the perceptron has to do classification, it goes through a hard threshold, something like this. So there are different versions of this, but something like this. So if the output at the summing stage is above 0 or greater than or equal to 0, then you output one of the classes, otherwise you output the other class. Now you might wonder what it means to be actually 0. We'll talk about that. So the way to think about this is that it's the hard thresholded output of the function weighted sum of the inputs. And often we use vector notation to simplify that, so we have this represented as a dot product. Now here, again, this could be 0, so it's arbitrary what you decide to do with a case that's on 0. From your knowledge of linear models, what does it mean when the output of this would be equal to 0? Anybody? Infinite solutions in what sense? No, okay. It just means it's on the line, right? Remember, I'm going to show you a little bit of a sort of geometric thing to try and build some intuitions in a second. Let's see. Actually, this might be the right time to do that. So let's, now I have to remember, people watching on the video, I think this needs to go on. So we need document camera, and that needs to go on the this projector 1, I think. Is it going on? Doesn't want to just go on. Okay, so let's try this. We'll put that on projector 2. Okay. Oh, it is there. All right, for those of you in the room, you can see both. For hopefully anyone on the video, you can see the pad. So let's go to the pad. Now there's a lot of, because perceptrons have been around for, whatever it is, 50 years or something. What year are we in, actually? What did we say that was? 1958. So we're in 2018. Isn't that 60 years? Yeah. Okay. So there's a lot of theory around this, and in fact, there was theory prior to the implementation of the idea. But I thought to kind of give you a quick sense of the theory. I just mention this idea. So there's an idea of a half space. Now this comes into theoretical characterization of linear discriminants, which is what we're talking about. And there are many linear discriminants. We had some at the beginning of this section. The basic idea is that, and we'll draw it in 2 dimensions. The basic idea is the following. So you have, oh dear, bad drawing. So you have a 2D setting, and I'll draw a linear discriminant just as a dashed line. And what we need, or the model that we need, is a vector, W, a vector of weights. These are the parameters of the model. And then typically we'd assume that we had class labels of points lying on one or the other side of the line. So half space, the space is simply that in general, 2 dimensions is not that interesting. We're dealing with a multi-dimensional, high-dimensional, possibly space. So the half space idea is that you have a decision boundary, and usually, as in the case of the perceptron and other things, you have a function which is the sign function, abbreviated like this, and depending on whether you're using homogeneous coordinates or you're just going from 1 to n for all of the inputs, it's going to have a specified offset or not. So b would be the offset. So this is just our familiar linear model. You could think of this as thresholding a y equals ax plus b type model, just as we had in linear regression, something of this nature. So the actual, this dashed line, what is it? It's a hyperplane in multiple dimensions, which is perpendicular to our weight vector. And our weight vector is, as we said, the thing that we had to learn. And it turns out that it will, this is not important to know, but in case you were wondering, it will intersect the vertical axis in 2D 0 minus b over W2, which is the second component of that. As I said, this is, I'll just put that in brackets because that's just an aside. So here's the intuition I thought it might be useful to make explicit. So if the input x, and I'll put this in natural language, shares an acute angle with the weights, then, so let's, should have formatted this better. So if then it is above the hyperplane. I'll put above in quotes because above in 2 dimensions is clear, but in multiple dimensions it may not be so obvious. And then you can probably imagine what the alternative is. So I'll just try and keep my coloring consistent. I'll just say if the angle is obtuse for the same things, then it is below. So here, by convention, we'd classify this as plus and the other one as minus. Okay, so so if we have, let's say, the space R to the 2, so two-dimensional real space. And in this case, we have two vectors. With this dot product formulation, we can express the angle between these two as the cosine, so the angle's theta, of x, which is our data point, and w, which is our perceptron weights, or whatever our model is, over the product of the two norm. Well, these are also vectors. So this is a way of making this angle statement operational. So let's see how that might actually look in practice. So I should just say, so where theta is this angle that we were talking about, the angle between x and w. X and w must not be 0, but otherwise it's okay. So let me try, I'm not very good at drawing this kind of thing, but let me try and sort of draw this. So something like we had, I'll move it down a bit, over here, and we had something like the following. Here was the hyperplane. Here was the vector, which is supposed to be roughly the same. It's not the best, but okay, so let's just pick a couple of examples for data points. So let's just sort of contrive it. So we'll say, let's say x1, and the color will give you a clue as to where this is going. So x1, we'll have the theta 1 at let's say theta 1 equals 70 degrees. So cos theta, so this is an acute, so cos theta will be approximately whatever, 0.34. And let's do another one, x2, theta 2 equals, I don't know, 120 cos theta is minus 0.5. So if we draw those angles, you get something like this. It'll probably be way off, but something like this might give you W1. Sorry, X1, and something like, I don't know, over here, it's going to give you X2. Okay, so the intuitive idea here is that you can tell which is going to be in which class by the angle of the x vector in either case with the weight vector that tells you what the model is. So essentially, the dot product idea is based on that intuition. Now, obviously, you've also got you've got the projection, which will tell you how much or where the projection of each point is going to end up, and that's going to be the actual value that you use to predict. That value itself is not used here, so you can get a plus prediction for anything that's positive, or non-negative actually, as we're showing here, otherwise a negative prediction. But in other kinds of linear discriminants, the actual size of the value, which is a projection of x, some point x on the weight vector, is useful information, and that value can be used both in learning and in prediction. But yeah, that's exactly what I'm talking about. Yeah, that's exactly what I'm talking about. So if it's under the boundary, then it's going to be classified. It's going to be classified below. But in this case, we're assuming that with that angle, it's going to. So this one cannot be classified as positive, right? So yeah. It could be, yeah. It could be. So it could be on W, but smaller magnitude. In which case, it's not going to be. That's right. That's right. That can happen, right? So this is not an exact statement of the perceptron. This is the intuition behind the perceptron. Now, what if they are orthogonal? Well, in that case, so if x and w are orthogonal, then x dot w, which is this thing here, is going to be 0 in that case. All right. Okay, so that's the model. So the model itself, let me just flip back to the slides. Wait a minute. So the model itself is something like this. So this is fine for anything that's linearly separable, but we've already mentioned the fact, I think we've already mentioned the fact, if not we will mention it now, that obviously many functions are not linearly separable. So here's one in this case that is not linearly separable. So in this setting, a perceptron's not going to work. So in the case of an AND function, so we can assume that if we have, let's say, 0, 0, 0, 1, 1, 0, 0, 1, and 1, 1, then we're going to have a linear separator somewhere around there. If we have XOR, a similar kind of thing, so 0, 0, 0, 1, in this case, you're going to have at least two, well, two would suffice in order to be able to separate these two sets of points. So XOR, which is this case here, you essentially have two regions which are separated by the other two regions of the positive class, and they're separated by the region of the negative class. So you're not going to be able to have a single linear separator here. And if you actually enumerate out even all of the Boolean functions of two variables, and certainly of more variables, you start to see that quite a small minority are actually linearly separable. That's not too bad, because there's an assumption, I think, that the typical kinds of problems that you want to address are, in fact, representable by linear separators. Even if they're not, there are linear separating functions that can do reasonably well if, for example, you have something that's approximately, something that's, I don't know, plus, and something like minus, something like this. So if you drew a linear separator through this, you might get something like this. So you're going to get some things wrong. There are versions of the perceptron won't converge unless it actually is linear separable, but there are other versions of things that are better able to handle this kind of thing, which we'll see. Okay, so some functions are not representable, they're not linearly separable. If they're not linearly separable, we need something else, and the classic example is to build multiple perceptrons, which is where the multi-layer perceptron comes in. So the key idea behind perceptron learning is finding a good set of weights. So how do we find a good set of weights? Well, we haven't seen, or we haven't looked in detail at this kind of scheme yet. So the linear regression kind of scheme is you have a closed form solution. You can derive what the minima expressions are, and you solve for that. That's not the case with the perceptron, but there's a general scheme that you can apply, which you can actually also apply to linear regression. I showed you a version of that, which is to incrementally move towards a set of weights that represent the function that you're trying to learn. So the weight update in perceptrons has some interesting features. It's dependent only on mistakes. So if you have a weight vector that works quite well, then you don't make any changes. And it's modulated or smoothed by a parameter called eta, the learning rate, which is typically less than 1. In the example, to simplify things, I'll sometimes assume that the learning rate is 1, because then essentially it goes away. Now, the interesting thing about the perceptron update rule, the perceptron training rule, which I'll show you an algorithm for, is that if the training data is linearly separable and eta is sufficiently small, then it will converge. The proof is has been around for a long time. It essentially depends on a few things, one of which is the amount of separation that you can get between the positives and the negatives, which is something called the margin, which we'll see more on later, but also the size of the examples, the magnitude of the vector of the largest example. But if you assume that all of the examples are bounded by a particular size, then essentially it comes down to being how much separation there is between the classes. So in some sense, how separable they are. So we won't do that, but what we will do is look at how the learning idea should work, should come about. So we'll say that there is a training set. So we'll assume that there is a linearly separable function, just to make life easier. We'll say that we have some examples in the training set, and we'll say that we start with a weight vector. For simplicity, you can imagine it's just a 0 weight vector, or it could be randomized with small values. And then at every point in the traverse through the data, we're going to have that we have a positive example in the first case, xi. If it's correctly classified by the weight vector, there's no learning to be done. Why change anything that works well? If it is misclassified, then we have to do something. We have to change the weight vector. So how should that change? So in the setting that we've got, so we said that xi was a positive example that was misclassified. So that must mean that the label yi, the corresponding label, is +1. And it must also mean that w.xi is less than t. Now, t is a threshold, and there are different ways of getting t. In the version that we are looking at, t was 0, but you know, depending on the setup, that can vary. Let's assume that it's simply the threshold. You can assume it's 0 for simplicity. So the goal of the learning is to update w to w prime, so that w prime dotted with xi is bigger than w dot xi. Why? Well, let's think about what the problem is. We said that it's misclassified. We said that w dot xi is less than t. We said that it's positive. So we know that w dot xi should be what? Greater than t, yeah. Greater than or equal to or greater than. So this is correct. This is a correct statement. So this specifies what we want to happen. So all we say at this point is that it should be greater than. It should move the decision boundary towards and hopefully past xi. Okay, so that xi would now be on the right side of the boundary. So the way to see this is that xi is on the wrong side of the boundary. The boundary has to shift towards xi. And xi being positive, we can imagine that it has to shift in the positive direction. Okay, so one way to do this is to set the new weight vector, w prime, to be the old weight vector plus the data point. Okay, so the data point itself times the learning rate. Let's ignore the learning rate for the moment. But adding this to this weight vector. So if this is added, then w prime dot xi will equal w dot xi plus itself, modulo the learning rate, but we can assume that it's set to 1. W dot xi plus the learning rate xi dot xi, which is now going to be greater than w dot xi. Okay, so xi dot xi is going to increase this thing here, and that fulfills the spec that we wanted here. So that's the positive example. So there's an opposite case where xi is misclassified, but it's negative. So we know the same two things in the other direction. So we know that its class value is, its label is -1. It's, when plugged into the weight vector, going to give you a result which is above the threshold, which is wrong because it's a negative example. So we know that it needs to decrease. W prime, W minus learning rate times xj. We set this equal to the old weight vector minus this, which is now going to be less than this. So now we have something interesting, because we have two cases which are sort of equal and opposite, and we've done the same thing essentially in getting an update. And the only thing that differs is the sign of the update. But actually we know what the sign of the update is, because it's either +1 or -1, depending on whether we misclassified a positive, in which case we add, or we misclassified a negative, in which case we subtract. So yi can be substituted in here to determine the sign. So this update is simplified into a single update rule. So yi acts to change the sign of the update, as we said, and this is the the core of the perceptron algorithm. So all the algorithm has to do is go over the training examples, and for each time there's a misclassification, it has to apply the update until all of the examples are correctly classified. Now, the interesting thing about this is that this will be, as we said, bounded by two things, essentially the amount of distance between the two classes and the size of the, essentially the size of the largest X vector in the data set. So here's the algorithm. The algorithm is just essentially the update rule. So we start off, in this case, we initialize. While it is not converged, we keep going. So D is the data set size. D is the data set, so from the first one to the last one, we do the prediction. So this is actually an interesting form of prediction. I won't go into it now, but essentially what you're trying to do is predict the class value without having the class value, and then you're told what the class value is. So this is a condensed version of this. So basically, remember, we were plugging in xi to the weight vector, and we were thresholding it and seeing whether or not it was plus or minus 1. And then, since we know what yi is, it's either the same as or it's not. If it's not the same, and you should just check that you agree that this will give you what that is. Okay, this is just a one-line version of that. If that's not the case, so this is a mistake, then you do the update. And the update is the rule that we just derived before. Now, we know if this condition has succeeded, then there's learning to be done because we've had a misclassification, so converged is false, and so we keep going. So converged is true when? When's converged true? Yeah, if you go through the whole data set and you don't modify it. All right, any questions about this perceptron training? How you determine the learning rate? Well, there's no sort of way of determining the learning rate other than sort of saying it should be, you know, typically between 0 and 1, usually sort of small, close to 0. If you're asking, is there any theory? No. Well, okay, let me say this. So in the convergence proof, the learning rate has a role, but it's usually assumed to be exactly what I said. There is a reason why you want the learning rate to be not too big, which is the following. Well, let's just look at this update. So what would happen potentially if you increase the learning rate? Well, you have to sort of wave your hands a bit, I guess. But if you think about it, what is the learning rate doing? It's modulating the movement of the decision boundary in one or other direction. So what you want to do is not move the decision, it's sort of heuristically move the decision boundary a reasonable amount on each mistake, but not too much. Now, there are smarter rules where so I should say this is about the most elementary version. So one thing you could say, if you're interested in learning rates, is one thing you could say is you could vary the learning rate depending on how many mistakes you make. Why would that be a good idea? Well, you might say initially, when you're making a lot of mistakes, you want to move the decision boundary quite a lot. Okay. Then, as you see more data and hopefully you start making fewer mistakes, you reduce the learning rate because hopefully you're closer to convergence and you don't want to screw things up. And certainly when you're training larger networks, that's a very standard thing to do. But with this, I think the easiest thing to do is to just imagine it's a reasonably small value, you know, sort of close to 0. But for the purposes of this, it suffices to essentially ignore the learning rate. I mean, theoretically, as I said, the learning rate is simply assumed to be somewhere between 0 and 1. Well, if you assume it's, no, you won't get the same solution. What you can say is something along the lines of the following: if you assume that there is a linear separating hyperplane, and you can assume that, well, you can go a bit further. You can assume that in some sense it's sort of optimal in this separation sense, right? So the optimal one, there are different ways of defining optimal, but one way in which you could define optimal is that there is no other separating hyperplane that is that has all the positives further away and all the negatives further away. That somehow sits between. And in that setting, depending on how large that separation can be, then you will get to that hyperplane. But no, if you change the learning rate, you know, you will potentially find a different one. But
probably going to end up with a boundary that's close to either plus or minus. That makes sense. There'll probably be a good gap in between.
The gap can be more than the distance between the separation.
Yeah.
the gap can be more than the distance between the. Sorry, what's your gap? What's the difference between the gap and the distance between the? Yeah.
This is kind of like a tunnel, right, between pluses and minuses, and all
Yes.
our models that would be valid would be inside this tunnel. So the maximum difference between any two models would be the distance of the tunnel.
Right. Yes. Yes. That's correct. I don't think that's what he was saying there.
No, it was like I was saying.
Oh, okay.
If you choose it too small, it will stop, and it could stop at a point where it's really closely.
Ah, right. Well, there's sort of two things: where it starts and what the learning rate is, depending on where it will stop. Okay, so you know, because you've got to take into account where it's moving from as well as where it's going to end up. So it could end up, yeah, closer to one than the other. That's right. But I mean, as far as I'm aware, there is no theory on how you derive it. Oh, no. There's theory on where the separating hyperplane should be. As far as I'm aware, there's no theory on how you derive the learning rate. Yeah.
Because learning the statistics about the data would actually already be like trained.
Yes, that's right.
No sense.
That's right.
learning that.
That's right, yeah. Okay, we're all good? Okay, I left that for you to work out, but we can quickly talk about it. How are we doing for time? All right, so just quickly, well, let's see. So we said that, what did we say? So if this is a positive, so this is the data, this is the label. So if this was positive, then w.xi should be, we're assuming homogeneous coordinates. So w.xi should be greater than or equal to 0. If that is in fact a negative, what's going to happen? Must be less than 0. If xi was labeled negative, but w.xi was greater than 0, what would happen? Right. So those two cases are the only mistakes, right? So in those two cases, it's going to be less than or equal to 0. And that is what you want, because you only want to do the update on the mistake. Yeah. Does that make sense? Is anyone else wondering about that? All clear about that? Okay. Okay, good. So, hi. So So there is a slide here about the learning rate. It's just, I think, what we're just talking about, just to illustrate that the learning rate is important. So it's time, I think, to just wrap this up and have a quick break. So what have we talked about? We've talked about distance-based and probabilistic methods, primarily naive Bayes, but we also took a divergence into some Bayesian stuff. We talked about logistic regression and the perceptron. All of these forms are more or less, or in some sense, linear models. In some of these cases, it's not exactly as obvious why they're linear models. The naive Bayes classifier can be shown to be a linear model. These are straightforwardly linear models. Why this would be linear could be, for example, if you were doing local regression or something like that. So along the way, so we've seen some actual methods. Along the way, we set the framework for classifiers, and a lot of these ideas are core ideas used in other classifiers that we'll see later on. Okay, so that's the end of that. Let's take our short break, and we'll get on to the next subject, which is decision trees.
Give me permission and I can try that while I'm still when I give the lecture.
Yeah, sure. I just need to. Can I set the password, because I need to. Because I'm currently using my own password, so.
Or do you need a SSH session?
Just do an SSH. Yeah.
Sure.
You still having a problem?
I need to double check.
In here? What?
Yeah, sure. Maybe, yes, just use. Don't need the command. Just username at.
Oh, okay.
So at
CSE?
Yeah.
Oh, okay.
CSE.us.wad.
Okay.
And then just open. I think it'll prompt for your password.
Okay. Oops. Okay, so that's me. So now we need to. Can I just do it from come online?
I'm not sure. Maybe
It should work, right? Oh, wait a minute. I've got. Sorry, can we do that again?
Yeah, sure. Logging in using.
Login is
Yeah.
wrong login.
So the first question one, this is the output, right?
Yes. So you got it working.
Yeah, finally. But
There you
how
go.
do I solve them as the eta output? Like, how do I output them?
Just copy paste into a file.
So,
No, there's no big deal. I think it says that.
And don't remember to include the first line.
which one?
I mean, this one you didn't include it.
This one?
Tried it. Yeah.
Okay, just this one. Start from data set. This
No.
one.
Everything. From the output.
This one?
Yeah.
Okay, so that's the output.
Yeah.
And I don't need to change the code.
No. Just copy that into a new text file.
That's
Save it
it.
as q1.out, and that's it. Don't worry, it's running. It's not waiting. Okay.
Okay, so you're in.
Yep.
So $work is the the current session stuff.
Yeah.
So you're in S1. If you want to go to where the files are, that's in public HTML 18 S1 S1. Oh, okay. What's I thought I put them in.
Test.py.
I thought
It is here. Test.py.
No, but I thought I put the test files as well. Oops. Okay, all the files you sent me are in that dr.tgz.
Okay.
So we can move that. If if you want them, they're in there.
Okay, sure.
I'll just have a quick word with these guys.
Where is the auto marking script? The main
That is in okay. Well, automark. You mean dry run?
Oh yeah, try.
Yeah. So that is so we're in. So the actual thing is in here. So we can go to there. Oops, no. That's wrong. So it's one. What? No, okay, wrong one. Yeah, okay, that was right. Okay, so I've commented. So the one that she wrote is this one here, or no, sorry. There are different versions. This is the most recent one. So you see, it's got the class name. Now I've got test.py down here. Okay, so I think one of the problems is that this is not going to execute anything. So I'm not sure what.
I'll try that. Try using Python 3 and things like that.
Well, that's what I think. So I think we have to say, user bin Python 3, that thing there, because this is just a.
Yeah.
I mean, the other thing you could try doing is putting the hashbang in the test.py, but that's what I started to do the other day, and that didn't seem to work. So
Okay, I'll try that.
I'm not sure. Yeah. So. Yes. Did you have a quick question?
Will you be posting material for? I presume the midterm is that happening still in?
I still need to figure. I think it's going to be week 6, but there's a big problem with rooms and
Sure.
labs and stuff. So
Sure.
I'll be confirming that in the next day or so.
Okay. Thank you very much.
Would that like just include what we get up to today?
Yes. Yeah. It won't go beyond today. Yeah.
Is there
It may not even include anything after Perceptrons. I'll have to see how far we get with this tree stuff.
will you release like a practice or something?
I'll release something. I'll release something that's representative. Yeah, we had a bit of a setback. We were trying to do something online, and that's just not going to work. So we have to go back to paper, which totally sucks, but there's nothing I can do about it. And even that's a problem because we've got more students than even fit in here. So it's a logistic problem, basically, that's been holding us up with everything else. But I will be letting you know, and I will put out some material.
Or extend her midterm? They're real tight.
Yeah, that's right.
Sorry to comment that it's under consideration.
Extension, yeah. I've considered it, and given all the input, I'm going to put it back to Wednesday. Yeah. If you're really stuck, then send me some email. Some people have got problems. Just let me know if you need more time.
Last year, it's a very different thing to what it would be this year because the structure's changed a bit.
It'll be the format will be like the kinds of questions. The structure will be the same. The content will be different. Yeah. Yes.
Even though I didn't run the file, it still have the output. So that's the output, right?
No.
Because,
You need to run it. Is this 2B? I mean, is this B, 2, question 2?
No, I mean, like question 1 I run, but you should wait for a very long time for my computer maybe. And like,
It shouldn't take that. It'll take some time because it has to do some work, but
yeah, and like this is because I didn't run the previous one. But like for the question 3, you see when
that's what you have to save.
yeah, like I didn't run the file and automatically have the answer on it. So I just not copy and paste for the output.
Copy and paste is okay, but that's what the output is. That's the model.
Okay.
There are two models, right? Or at least 2.
So
One
we don't-
before
we
and
don't
one.
need to change any code, right?
I can't remember exactly what the question says, but you need to do something, which is this transform. I don't think you need to The basic thing, I don't think you need to change any code. You're given an option to do more, but you don't have to. So the basic thing is a before and an after, and I think it's all there, but don't quote me because I can't remember it.
I think you talked about writing code to calculate one thing, but you could actually do it in a spreadsheet if you were so inclined.
You could, yes.
Yeah, I think I did it both ways.
Yes.
To cross-check.
Yeah, that's right. I did it in a spreadsheet as well.
Hi, Professor. You see, for the modified weight equal to this weight plus this one, but for here, modified weight equal to weight 2 y times like this, y items like this, but here there hasn't y. So I don't really understand what's the difference between this.
Okay, so how are we doing for time? Okay, let me quickly. Okay, yeah, I did a lock on. Okay, right. Okay, so you get the fact that you have to either increase it or so this has to go up and this one has to go down. So if you add this, then this W dash or W prime W prime is going to be W plus eta x. So that's W dot xi plus eta xi dot xi, right? Substitution. So that has to be more than this, okay? Just because, you know, I mean, this is going to be greater than that, because that, you know, that's even if x had some minus values in it, that's going to be, you know, it has to be positive, right? So it has to increase. The other way around is the same, but with subtraction, right? So W prime is now W minus eta xj.
Yes.
So W prime dot xj is W dot xj minus eta xj dot xj.
Yes.
And so this has to be positive, so this minus that must be less than itself.
Yes, yes.
Okay? If you've got that, right, so those are the two things that have to happen. Either it's a plus that was classified you know, too low, or a minus that was classified too high.
Yes.
But if you look at the form of this, sorry, if you look at the form of the update,
Yes.
where's the first one? Here's the first one. So W prime is W, the thing you had before, plus eta xi. We'll assume eta's 1, so W plus xi, or W minus xj, xi. So either you're adding or subtracting x, basically, the current x. So all this is saying is, well, we already know that in the case of a misclassified positive, we have to add. So the sign of, or y is +1. In the case of a misclassified negative, the sign is negative, so yj is negative.
Yes.
So we just multiply by y, and in both cases it's going to turn the sign in the right direction. So that will give us a single rule. That's all.
Yes.
So it's not really a big deal.
Yes.
Okay, makes sense?
Thank you. Makes sense.
Just wondered, are you going to give us some info about the exam?
I will. Not today, but because I'm trying to sort it out, but soon.
Can you tell me when the exam is going to happen?
Not yet, no, I can't, because I don't know. I have a logistic problem. I have too many students to fit into one lecture hall.
So does that mean it won't be the first week back after the break?
I can't say for definite yet.
All right.
Is that going to cause you a problem?
No, not really.
I'll be tomorrow, very soon, next couple of days. I'll know. I should know tomorrow, but I haven't been told yet. So, yeah.
Thank you.
So theoretically, week 6 in here plus somewhere else, but I need to confirm that. Okay, let's resume with introducing the following. Decision trees. We'll talk about the data and the models for which decision trees are the right choice. And then we'll introduce the basic algorithm, which is called TDIDT. So decision trees have been around for a long time. And there are different ways of learning decision trees, growing decision trees, but the one that's come to dominate is this top-down method. Now, we'll talk about a particular idea that I've referred to before, but I'll introduce it in more detail, called entropy. It's also related to another idea that we've seen, which is variance reduction, and I'll talk about that next time when I go over regression trees, which are an extension of decision trees. Then I'll talk about some important restrictions and limitations of decision trees, but also things that make it efficient and also comprehensible. So there's a trade-off in the inductive bias of this algorithm. And I'll also talk about how to deal with the problem of overfitting, because in representation like decision tree, there's a large capacity to fit data. So anytime you have anytime you have that property with a learning algorithm, then you are in danger of having some overfitting. So some of the ancillary issues which have been developed in decision tree technology will be addressed. And later on, we'll come back and revisit, once we've looked at a particular theoretical problem, we'll look at multiple ensembles of these trees constructed in a number of different ways to solve that problem. So, given the fact we're running a little late, I'll skip over some of the history. It's important that decision trees in practice, in some form or another, are extremely widely used and have been for a long time. Reasons for that is that the ideas behind them are intuitively clear. They're usually easy to implement. Once they're implemented, they're usually easy to use, and they're usually efficient. There are some drawbacks. They do tend to have what's called a high variance, and we'll get to that. That's an issue that we'll come back to. Fundamentally, they're designed to do classification, which we've just been looking at, but they can also do regression. So here's a simple decision tree. So we'll see it's as typical in computer science, it's a tree which grows from the root down to the leaves. It has tests on nodes in the internal to the tree, and at the leaves of the tree, it has so-called decision nodes. The tests, this is a very simple tree, so the tests are on a feature with a number of values. It can either go straight to a decision, or it can recursively descend and test another feature with more values and continue. In this case, it bottoms out after 2 tests in these 2 subtrees. Decision trees can also have a probabilistic representation, and in fact, mostly that's actually what's used. To try and illustrate this, here is an example in text format. So here we're seeing the tree represented horizontally from left to right. At the root of the tree and in each subnode, we can see that we have labeled data, and we can see that this defines an empirical distribution. So we have, in this case, 1,000 patients. We have most of them in the plus class, and that gives a distribution of roughly 80 to 20 positive to negative. So that's before any prediction has taken place. And then the decision tree recursively descends, and we'll see how this is done. And at each point, it successively refines the data into smaller classes. So we go from 1,000 here into a slightly smaller subset here. And by the time we get to the leaves, we've got much reduced data set sizes. At each point, we are testing a feature either for a numeric value being above or below a threshold, or some binary decision, or indeed some other kind of attribute value type test. At the leaves, and in fact at every node, you can do a class prediction based on the probability. And that's quite important, because that means that the tree can either be fully grown or it can be partially grown. But at any point, you can make a class probability prediction. Every node has the capacity to do that. So this is a little bit fuzzy. This is a snapshot of a commercial system, but essentially the information is identical to the ASCII text version I showed you on the previous slide. We have two classes. There's a class distribution here shown by the colored histogram. So we can see here that as the tree algorithm has built the tree, the class distribution at each node, which captures the subset of data in question, has changed, or potentially can change. So here the blue class has relatively increased in size with respect to the green class, whilst over here it's the opposite. Okay, so this is a pictorial representation of that probabilistic information that we had before. And here is the famous IRIS data set showing similar kind of information. So the IRIS data set is all numeric values. There are actually 4 features. So here we're showing that at the root of the tree there are 150 examples. They are divided into 3 classes. And there's a value of a measure here. This is the Gini measure. We haven't seen what that is yet, but we will. There's actually a class ascribed here, although the basis on which that's done is not clear because, it's not clear why this class would be preferred. It seems to be that all of the samples are there, so why this would, I guess, be some sort of default. As we descend the tree, we shuffle the data according to a particular test. So this value here thresholds one of the features, and this, it turns out, gathers all of the examples with one class into this subtree, and this then becomes a decision node. So there's an idea here about the relative frequency of the classes, and that idea is represented in a concept called purity. So here we have a pure node because there are only examples of one class. That class is this out of the 3 classes. Over here, this is an impure node because we have still samples of 2 classes. Now note here that there's actually, the tree is actually giving a prediction at every node, as I pointed out before. The basis on which you can do that is, well, there can be different criteria, but one could be the majority class. In this case, it must be an arbitrary decision because there are 2 classes, each have equal numbers of representatives. Further down the tree, you can see that the size of these subsets is drastically reduced, but all of the examples in the first class are captured already, so that's immediately gone to a decision node. And as you descend the tree, you can see that fewer and fewer examples are turning up. So these are somehow special cases that are processed further and further down the tree. So we can see a few things. I already mentioned that you can get a prediction at any node. So in fact, you can terminate tree growing or prune back tree growing to any depth, and you will be able to get decisions. The quality of those decisions is a bit variable, though. So in some cases, they're going to be based on a lot of data, as up here. In other cases, they're way down to single examples. So decisions at lower levels of the tree may be something you want to be a little bit cautious about because they're based on less data. However, it may be in your application that you need specific cases to be shown up, and this will continue, or potentially you will be able to continue growing the tree until that's actually the case. So let's think about this representation very quickly. So clearly we have a tree. What is a tree in terms of expression? So if we think about it as a logical set of statements, we can think about representations for some basic Boolean functions, such as the classic binary ones, or even more complicated statements. But then we can also think of something like a threshold function. So how does a tree represent these elementary ideas? Well, for simple Boolean concepts, you can see here what it's doing. It's actually simply enumerating the conditions under which a prediction is made. So prediction is either based on the attribute values true, this is a decision, or not. And we have to check, in this case, the truth values of these attributes. But notice here something important, that there is an order to the structure of the expression. So first we have to pick one of the Boolean variables. We check its truth value. Depending on that, we descend to another one. If we look at another expression, we can see the effect of that. So if we pick this one here, we can immediately bottom out in a decision. And then we have to test conditional on the other values. The other value. We have to test the values of the other variable. That's fine. And one advantage of this is you can think of things like XOR as being just as easily representable in some sense as these simple Boolean functions, which is not the case, as we've seen, for linear models, which are essentially doing the same thing on logical data. However, when we look at a concept like this, we can start to see one of the issues. So this is the function that is true when 2 of the 3 inputs are true. So what we have to do here is, because each feature is enumerated in some kind of order, we have to test the cases under which X being true or false could contribute to 2 out of 3 things being true or false. Now, one disadvantage of this is that if you think about something like a threshold function like a perceptron, it doesn't really care. It doesn't really care which, let's say it had 3 X inputs. It doesn't, and it was trying to learn 2 out of 3. It doesn't really care whether or not it's the first one and the second one that are true, and the third one is false, or the first and the third are true, and the second one is false. As long as 2 out of 3 are true, and the weights are in the right direction, it should succeed. But decision trees have to carefully enumerate the cases under which these are true. So the bias for decision trees is towards, I think, short statements in which the key features can give most of the predictive power quickly. Another way of thinking about it is that they represent a disjunction of conjunctive statements, which together, if they are true, will give the prediction. And this generalizes to multiple values. So if they're a Boolean function and there are 2 to the d possible inputs, so any Boolean function can be represented by a tree, and each function says it's true for one of the 2 to the d possible values. Okay, in the worst case, the representation, as we saw with things like M of n, can become highly complex, so enumerating out all of these conditions. Good examples of these are things like parity. Now, parity is an important one, parity and XOR type things. parity and XOR type things are hard in general for systems that are uniform in structure in a particular sense to learn. So parity, which is a version of XOR, is hard for threshold functions like perceptrons. It's hard for decision trees. You can get around it, though. So just as a heads up, you can get around it by, for threshold functions, adding in multiple layers. For other functions, you can get around it by essentially changing the way in which the logical expression works. I won't go into exactly how you do that, but there are different ways to do that. Essentially, adding more structure. So I guess the takeaway of these slides is that although in principle you may be able to represent the function, the complexity of representing it may mean that in practice, particularly if you don't have a lot of data or a lot of time, then it may be hard to learn. So when do you think, when should you consider decision trees? When would they be a good idea? One nice thing, there are a number of nice things that they do out of the box. One is that you can use numeric features and discrete features in the same data set. You are doing classification, so you have to have a discrete value, although you can use regression trees to predict a number. As we've just argued, if the hypothesis has sort of multiple structures, substructures in it, then this is a good thing, like disjunctions. Decision trees are quite good with noisy data, so they have a built-in overfitting avoidance bias. The key feature that's usually cited is that they're interpretable, and what we mean by that is you can read them off in a rule sense, and they're quite widely used in financial applications, in medical applications for this kind of thing. Okay, so the basic algorithm is this, very straightforward. So we already got the idea of what a tree looks like, right? And how we understand the tree is to go from the root to the leaves in a recursive fashion, right? So here's the whole data set. If we fix one feature or attribute and say what the conditions are on that, then this will split the data, and then we go recursively down to the sub data sets, which are in those splits, and we continue doing that. So that's the structure of the tree, and the learning method for the tree comes straight out of that, because the attribute is selected as the best for the current situation in the tree. This is assigned as the current fixed attribute for that position in the tree, and then for each value, you recursively descend into the node, and you sort the training examples all the way down. If at any node, so we've now created a new subtree with a number of nodes, and they're leaf nodes because we've created them in one step, they contain data. If we look at the data set, the distribution of the classes on the data in that data set, they could be all of the same class, in which case we say they are pure, the node is pure and the examples are perfectly classified. In that case, we don't need to do any more work because we now have a path from the root to this leaf that perfectly predicts for that subset of data, and then we stop. So if you think back to the, well, let me just flip back to the iris tree, which was here. So in one step, you've managed to identify by setting this condition. We won't say exactly how this was done, but it was done. And now in one step, you've got a decision node. And there are no descendants here, no descendants of this node. On the other hand, you could have got to this point, and there's still more work to do because you've got a mix of classes. So there's a 50-50 split between the classes in that set of data, and you need to do more work. So you recursively apply, you iterate over the new leaf nodes, and you call the algorithm again. Now this algorithm has appeared in many guises over the years. Different people have proposed it. There are many ways to do the different choices in this algorithm. And then this is going to give you a tree of some kind. And most of the work that's been done is to try and figure out, what's the right way to make these choices. The one I'm showing you here is often referred to as ID3. It was developed by Ross Quinlan, who was a professor at Sydney University. The publication was in the first issue of the Machine Learning Journal in 1986. And it was very widely applied and has continued, or the basic ideas have continued to be applied in more recent upgrades of that. So it's a symbolic machine learning algorithm because the way we've described it, there are no, we haven't used any ideas about geometry, we haven't used any ideas about probability. It's simply this recursive splitting of the data. Around about the same time, four statisticians based at Stanford and Berkeley developed a decision tree learning algorithm that was very, very closely related to ID3. It was called CART, which stands for Classification and Regression Trees. And over the ensuing period, lots of research has been done on different permutations of these same basic ideas. The state of the art at the moment is that an algorithm essentially like this is the core of all decision tree learning algorithms. So either you trace its antecedents to ID3 or CART, but the ideas have basically been established. Okay, so we've now got some design decisions because the algorithm as such is only informally defined. So the first design decision is we have to choose a feature or an attribute at the current node. So this is a greedy algorithm. It goes node by node in the tree, and at each point it makes a decision and continues with that. So here's a decision point. So in this node, we have to assign some feature. So here we've got two things, A1 and A2. They're attributes or features. And we need to know which one to select. Now, at this point, we have a data set. It has a class distribution. Here's a two-class version. So on the basis of this data, there's nothing that we can decide. What we have to do is look ahead. We have to say, well, if we chose this attribute, and let's say they're both Boolean or binary, true or false values, they could be numeric, doesn't matter. If we chose this one, what would happen? Well, it would recursively split the data into two new nodes, which could themselves end up being trees. But the next step is to sort all of the values, all of the data according to the value of this attribute. Is it true for each data item here and here? Is it false? If we were to do that, we would find that out of the 29 positives, 21 had the value true. 5 of the negatives also had the value true. Out of the 35 negatives, I beg your pardon, let me rephrase that. Out of all of this data, 21 of the 29 positives had this value true. 5 out of the 35 negatives had the value true. Out of this set of data, 8 of the positives and 30 of the negatives had the value false. Sorry, it's getting close to the end of the lecture. A verbal stumble or two may occur. Right, if this one was the choice, an analogous but different outcome would happen. So we've got 18 out of the 29 positives having the value true for this attribute. 11, the remaining 11, let's see, does that add up to 29? Yes, it does, 18 plus 11. Okay, so this subset is split this way, and this subset of the negatives is split this way. All right, so how do we understand the quality of each of these alternatives? Well, there are a number of things we could do. What's actually typically done is the following. And to sort out what's typically done, let's take a quick digression. So the idea is based on information theory, which I mentioned last week. The idea behind the information theory model here is quite straightforward. So we have random samples, and then we say we can determine the probability. We assume in this case that they're only going to have a certain number of discrete values, but that's not a restriction because this can work for numeric values as well. So let's say we want to decide on what the information content of any signal containing these symbols that are distributed according to this distribution is. Now we make certain assumptions. Usually a simplifying assumption is that there's a restriction on the channel capacity, and so there has to be an encoding. So the restriction here is that it's binary, also happens to be serial, but it's binary, so we have to choose a binary code. The serial part means that we have to be careful so that the code can be decoded unambiguously. So we will always know that a certain code will give us an A as opposed to a C, for example. So we have to turn this into a string of bits. Now the probabilities here were equal. So a natural thing to do would be just to give them uniform probability, and then a natural thing to do would be to give each symbol a code like this. So you know that every symbol has a 2-bit code. If you had a different distribution, which here we're showing a non-uniform distribution, it turns out that it's possible to invent a coding that uses less than 2 bits on average. How could that be? We've got 4 symbols, so you'd naturally think that we need 4, we need 2 bits for each, because we've got 4 possibilities. So on average, transmitting any symbol would require 2 bits if we have a 2-bit code. But it turns out we can do better than that. And we can do better than that because we can encode according to the probability. The probability of some symbols is higher than others. So we might say the following. Well, if it's more likely to see one symbol than another, how about giving the more likely symbol, the more probable symbol, a shorter code, because we're going to have to write it down more often, or we're going to have to encode and decode it more often. And so that's what is done here. So we're assuming, based on the probability, we're assuming this is the one that's most likely. So we give that the shortest code, and then this, and then these other 2, which are less likely. There are many ways, alternative to this, to achieve this kind of coding. But the important point is that we've reduced the complexity, if you like, of encoding the signal. This seems like a small reduction, 1.75 bits per symbol on average, right? So that's important. It's if you send lots of messages, all containing these symbols distributed according to this distribution, this is on average what you'll get. But that, on average, could be useful, particularly if messages are, so if there's a lot of data. If you are wondering whether this applies to coding only non-uniform probabilities, well, the answer is actually no, it doesn't. So here we have a uniform probability. A naive coding would do what we did before, which would have 2 bits per symbol. But in fact, it turns out that, as before, you can get a code by using the same sort of hierarchical coding idea. And on average, this will give us fewer bits, and here's the explanation. I'll leave that for you to confirm for yourself that that's okay. And here's the general statement of what we've been introducing. So the general statement is, if we know the probability of the event, and we've been talking about symbols being transmitted, but this is a more general idea. If we know the probability of this event, which in this case is transmitting an A versus a B, then we can say that the optimal number of bits to encode the symbol in the sense that we've been talking about is minus log to the base 2 of the probability. We won't go into why that's the case. Probably some of you have seen this. Many of you probably have seen it. But in this case, every symbol has the same probability, so we have this, which is a little less than the 1.6 that we set out to have. Okay, so now we have this notion here. The smallest possible number of bits, on average, if we have m possible values for the random variable x. The smallest possible coding is this thing here. This quantity is called the entropy, typically denoted h of x. The entropy is the probability, log to the base 2 of the probability. We take because the log of a probability will be negative, we take that negative, and then we multiply this by the probability to normalize over these. So as a summation, it's sum over the m values that the discrete random variable can take, and the entropy is negative pj log 2 pj. Okay, what's this got to do with decision trees? Well, high entropy for a random variable we can think of as no variation or little variation or uniform, or I've said here boring, but not much change really, or not much differentiation. Low entropy, on the other hand, means the opposite. It means there is some change, so we're not seeing uniform probabilities, and this may be interesting. So why does this work? Well, if we think about the task that we have to assign values to nodes, we can cast it, here it's shown for a two-class problem, we can cast it as follows. We have a sample of training data, we have a split, and then, as we saw before, we have to look at the distribution on the split. So here we have just positive and negative. Now it turns out that entropy has this shape of function. So in the middle, as we said, we have maximum entropy, right? The two samples have the same class, the class distribution is the same for the sample. But if we have a skew, either to one or the other, and this is symmetric, so we're just showing one, the positive, then we have much lower entropy. So if the probability is close to 1 or the probability is close to 0 of this class and vice versa the other class, then we have low entropy. Why might that be useful? Time's short, so I'll make that a rhetorical question. Well, entropy is a measure of impurity, and remember we said that impurity is the thing that we want. So impurity can mean one in which all of the samples are of the same class. Sorry, did I say impurity? I meant purity. So least impurity. Okay, so this simply says the same